All right, 801. Let's start. Here we go. Use substitution again. So you're gonna have a class today. Make sure to get it done by tonight. That's the only thing. Okay. So let's jump right into a warm-up use substitution problem. All right. So we want to find the indefinite integral of 3 times 3x minus 1 to the fourth with respect to x. All right, so first question we should ask is, do I know just a simple function that has this as its derivative? I don't. I don't know about you guys, but I don't. So what should we do here?
Use substitution.
I'm going to use a use substitution. That's right. And what is u going to be?
3x minus 1.
Good. 3x minus 1. So that du is what? 3 dx. Okay, or if you want, again, you could say, this is the same thing as saying du dx is 3, and then move the dx over. That's really all we're doing. Okay, all right, so this is u to the fourth, 3 dx. Well, that's du. Not a whole lot we need to do extra here. So this is equal to the integral of u to the fourth times 3 dx. Well, again, that's du. Now, something I should mention, some people like to, instead of finding the right number to multiply du by, some people like to just solve for dx and then just plug in what you get for dx. And dx is normally going to have x's, right? And so the only downside for that is if you have x's left over, then you have to solve u, or this equation for x, and plug that in, which is sometimes necessary. Sometimes there's no way around that. We're really looking at only some of the nicest integrals that you can use substitution on. But use substitution can be used on a lot more complicated integrals to give you something very important. Oh, wow. Yes, Saba, that's exactly what we could do. I didn't know you asked that before I started saying that. That's funny. But yes, you could solve for dx and plug that in. And when you do that, we would get 3 times 3x minus 1 to the fourth is u to the fourth, and dx is du over 3, and then cancel. And we end up with this. Okay. So what's an antiderivative of u to the fourth? Good, u to the fifth over 5 plus some constant. And then now I need to substitute back in for u. So that's going to give me 3x minus 1 to the fifth divided by 5 plus some constant. Yeah, absolutely. You could write this as 1/5 times 3x minus 1 to the fifth. Absolutely. Okay. Is it possible that dx will make a problem? Yes, it's absolutely possible that dx could give you something that it doesn't perfectly solve for what's left over. And then in that case, you would need to solve for x and plug in x in terms of u. Okay. I'm not going to show an example like that today, but when we come back, I'll show you, the first day we come back, I'll show you some more complex examples of u substitution. Okay. So that last example illustrates, the previous example illustrates, nailed it, the general power rule for integration. Okay, so if g is a differentiable function of x, then we have the integral of g to the n times g prime with respect to x is g to the n plus 1 over n plus 1 plus c, as long as n isn't equal to minus 1. Okay, Or if you let u equal g of x, then this integral right here just becomes this, and you get that, right? So this is the general power rule for integration. And I mean, you don't really need to prove it. To prove it, you can differentiate this side of the equation, right? And check and make sure that this is what you get. And that is what you get when you use the chain rule, okay? So let's use this. Find the integral of x plus e to the 3x. Is this something new to u substitution? No, this is just a specific application of u substitution, this general power rule. So let's find this integral, the integral of x plus e to the 3x. How am I going to do this? Distribute. Yeah, she's on it. Yeah, you got it, Saba. I tried to trick you guys, and I didn't trick anyone. Yeah, first of all, this isn't some function times its derivative or some multiple of that, right? So, but always remember that you can break up the integral of a sum into a sum of integrals, okay? This is the same thing as the integral of x with respect to x plus the integral of e to the 3x with respect to x. Okay? So this first guy, I don't even need a u substitution for that, right? So what is the integral of x with respect to x? Ooh, careful, that's a derivative. Yeah, so we're going to get x squared over 2 for that first guy. Now for this dude, we're going to look at what rule do we need to use? Yeah, or the opposite of the chain rule, right? This is a u substitution problem. So, but again, they're cut from the same cloth. So I need to let u be something. What is u going to be? What was it? 3x, yeah, perfect. 3x. And then du is what? 3dx. And so again, if you want, you can solve for dx as 1/3 du. Or you could think of it as trying to multiply du by the right thing to end up with what's left over, but here that is just dx. And so when you do that, this becomes plus the integral of, well, e to the 3x, that's e to the u. dx is 1/3 du. Okay. So this is equal to, well, x squared over 2 isn't going anywhere. That's just from that first integral. Plus 1/3 times, what's the integral of e to the u with respect to u? What's special about e to the u? Yeah, we get e to the u back, right? E to the u plus some constant. But now I have something with x's mixed up with u's. That's not good. So I'm going to rewrite this as x squared over 2 plus 1/3 times e to the u, well, u was 3x. So this is e to the 3x plus c, right? And lastly, if you want to distribute stuff, you end up with this. Again, remember that 1/3 times c is just another arbitrary constant. And so most people, when they distribute that 1/3, just say my 1/3 times c. I'm just calling that c again. Okay. So this is our answer here. Any questions on this? U substitution. All right, let's look at this one. The integral of the natural log of x squared divided by x with respect to x. All right, so again, first question you should always ask yourself is this just some simple derivative of some other function I know? Answer is obviously no. So what should I do here? Well, if I'm looking at the integral of some composition, then what would be the inside function here? Well, if it's just x, you never really want to make the u substitution u equals x because that's not really going to change anything. That's just going to rewrite everything in terms of, that would just be natural log of u squared divided by u, u. Yeah. Yeah, that's exactly right. That's exactly what it is. Yeah, that's the inside function here, is I have something, some function inside of the other function squaring, right? So I'm going to let u be the natural log of x. Then what is du? You think of it as what is du dx? Remembers what's the derivative of natural log of x? Someone other than Saba. Yes, of course you got it, Saba. Someone online.
1 over x.
Perfect. 1 over x. That's exactly right. So then we rewrite this. I can say that du is 1 over x dx, which is exactly what's left here. Or again, you could solve just for dx if you want. And write dx is x du. Okay. Sometimes you have to do this. Sometimes you have to solve for dx. Sometimes really the u substitution is less about changing to u and more about, or it's less about making the integral simpler and more just about maybe getting rid of some square roots or something like that. So u substitution, again, can be used in a variety of ways. So, but either way, however you want to look at this, this becomes the integral of, well, natural log of x squared. Natural log of x is u, so I'm going to get u squared. And then dx is x du, so I have u squared over x times x du, or if you want, again, you could just write dx over x is du. Either way, you're just left with the integral of u squared du. Well, the integral of u squared with respect to u is equal to what? U is natural log of x, but the integral of u squared is what?
just u to the third over 3.
No, you're fine. Yeah, exactly right. U to the third over 3 plus some constant. And now, again, remember, U substitution is like changing languages to think about the integral, and it's something that's more natural, but now we have to substitute back an answer in the language we were asked, which was in terms of x. Okay. Yeah.
When we're doing these,
Mhm.
like we have u squared du.
Yeah.
That just falls away every time. Because like we didn't plug that in what du was for just one over x. Yeah.
No, we plugged that in. We plugged in du is, we thought of dx as, either way, you can think of it in terms of either of these things. But either way, your final integral has to be either in terms of only u or in terms of only x. Yeah. Yeah. Any other questions? Good question. Yeah, someone asked, are we still thinking about the integral as the area under the curve? Yes, ultimately the definite integral is the area under the curve. With u substitution, this is going to help us find areas under more complicated curves, because we could, on this last example, actually on the next example, nope, I'm wrong. I'm going to skip that one actually. We're going to go straight to this example here. On this example, we have a definite integral of something that we don't know, that something that pretty clearly requires a u substitution to find that antiderivative. Okay, so u substitution is a way for us to find areas under more complicated curves. Okay. All right, so let's do this integral here. So first of all, if I want to integrate something from -1 to 1, I need by the fundamental theorem of calculus, I need an antiderivative of that thing inside the integral. So first, step 1, I'm going to forget about the bounds for a second. First, I'm just going to try to find an indefinite integral of x squared cosine of x cubed to use with the fundamental theorem of calculus. So first, I'm going to find the indefinite integral x squared cosine of x cubed dx. Then once I find that, then whatever I get, I can say, well, if this is capital F of x, then I can just say this is capital F of 1 minus capital F of minus 1, right? So let's find this. This is pretty clearly, because we have a composition of functions going on, u substitution. What should u be here?
X cubed.
X cubed, very good. X cubed. Then what is du?
3x squared.
3x squared dx. Yeah, very good. 3x squared dx. Okay. So again, you can think of this two ways. If I just multiply this by 1/3, then I'll have exactly x squared dx left. Or you can just think of, if I solve this for dx, this is 1 over 3x squared du. Either way, when I plug into the integral, I need to have something that's only u's after I make the substitution. Okay, so I'm going to get, when I do this u substitution, I'm going to get, well, cosine of x cubed, that's cosine of u. I'll leave this x squared out here for a second. And dx is 1 over 3x squared du. So then notice x squared cancels with x squared. And I'm left with the antiderivative, or sorry, the indefinite integral of 1/3 cosine of u du. Okay. Questions on that? All right, well, what is 1/3 times the indefinite integral of cosine of u du?
Sine u.
Yeah, perfect. Sine of u. Technically plus a c. For this problem, because I'm going to find a definite integral, it's really not important to have the plus c. But for completeness, I'm going to have it there. And now I'm going to have 1/3 times sine of, well, remember, u was x cubed. Okay, plus c. So this is an antiderivative of this thing inside the integral. So now I'm going to do this. Okay, so now I plug in the integral from -1 to 1 of x squared cosine of x cubed dx. Well, this is going to be equal to when I plug in 1 and -1 into this guy and take a difference. So this is equal to 1/3 times the sine of +1 minus 1/3 times the sine of -1. And I should put this in parentheses technically. Okay. Questions so far? Technically, we're done. I'm going to do a little bit of simplifying. So, something special about sine of x is that the sine of negative, for any x, the sine of negative x is equal to negative sine of x. This is this just means sine is what's called an odd function. Okay, it's symmetric about the origin. Okay, so this then using that fact, this is 1/3 times the sine of 1 minus, well, this -1 can come out in front when it's inside of a sine, right? So this is minus 1/3 times the sine of 1. So this is really 1/3 times the sine of 1 plus 1/3 times the sine of 1, which is 2/3 times the sine of 1. Right? So there's that answer. So if we look at Desmos, we were looking at x squared cosine of x to the third. No, that's wrong. What were we looking at? Sorry. Oh, no, I was right. How dare you guys make me question myself. Cosine of x to the third. Beautiful. And we wanted to find the area under this thing between, come on, there we go, between x equals plus and minus 1. Perfect. Okay, so we wanted to find the area under that guy. Zoom in vertically a little bit. Okay, and that's exactly what we did. We found that area using a definite integral. Okay, but I mean, look at this, how crazy this function is. We plugged in plus or minus 1, but we can find the integral under, we know the the fundamental theorem of calculus. Give me any two endpoints and I can find the area under this really super weird curve, right? So that's that. And then the sine of 1 is not a rational number. Sine of 1 is just about 0.84147. If you typed sine of 1 into another calculator and it gave you something really, really close to 0, that means your calculator's in degrees and you need to change that because in calculus we use radians. We're radian people now, okay? Can you find the area in Desmos? Yes, you actually can. In Desmos, you can say, you just type int, and then you go, then that gives you the integral sign, and then this is -1. You type in +1 up here, and then you do x squared times function cosine x to the third. Oh, get out of here. Times cosine x to the third, and then you just have to say dx, and it gives you 0.5609. And then if I come up here and type in sine of 1 times 2/3 to check and make sure I'm right, look at that, I am right. We're right. We got there together. Okay. So that's that. Any questions on this? Yeah.
For the last problem,
Mhm.
you did L11X, you did U squared U, and then it became antiderivative cubed over 3.
Yeah.
Why didn't you do that the first time? Because it was just U. You didn't do U squared over 3.
We got cosine of u.
So it was just changing it to sign, we couldn't change the U because it was
Mm-mm.
a function of.
Exactly. Yeah, we want the right-hand side, we want to get something that is when I take the derivative, I get this. And that's just sine of u. Yep, no problem. So this process, I'm about to introduce something that you guys are going to think is way harder than what we just did, or is more confusing. And when I first learned it, I agreed. I hated doing definite integrals with u substitution this way. I preferred first finding the indefinite integral in terms of x and then plugging in my numbers. But in real life, it's a lot easier once you get used to it. It's a lot easier to just change not only the integrand, the thing that you're integrating, the function you're integrating, to u. It's also much easier to also change the bounds in terms of u, okay? So, sine of 1 is not 0, in case anybody thinks that for the last problem. Sine of 1 is about 0.8, okay? So, this theorem here is about how do we change, if I have a definite integral that the integrand requires u substitution, how can I shortcut first finding the antiderivative in terms of x and then plugging in plus and minus whatever? How can I shortcut just to doing everything in terms of u? That's what this theorem tells us, okay? And the way we do it is just by, once you make the u substitution, u is equal to g of x. Well, then if the integral in terms of x is going from a to b, well, then you just plug in x equals a and x equals b into this to find out where u is going between, okay? So let's use that here. Let's use that to evaluate the integral of x times e to the minus x squared over 2 dx. Okay, the integral from -2 to 2. All right, so first, is that a function whose antiderivative you just know? No. So this looks like it's probably going to be a u substitution problem. What should u be?
Negative x squared over 2.
Yeah, exactly. Negative x squared over 2, right? And what's du going to be? Or du dx, if you'd rather. What's the derivative of u with respect to x? Well, what's the derivative of?
Just negative x.
Yeah, perfect. It's just negative x. Very good. Negative x. Okay. So again, we can say that du is negative x dx, or we could solve for dx and hope that everything cancels when I plug in. And when you do that, you get dx is negative du over x, okay? Either way. All right, so the one other thing that we're going to do now, this is a definite integral. I don't want to have to do all the work of finding the antiderivative first, then coming back and plugging in. I just want to jump straight to another definite integral. Okay, so this is equal to, it's going to be an integral from somewhere to somewhere of, well, x e to the negative x squared over 2 is u, and dx is negative du over x, right? Oopsies. So the x's pretty clearly cancel. And I'm left with negative, I'm going to fill in these bounds in a second, negative integral of e to the u du. Okay, so if my original bounds in terms of x go from -2 to +2, then what should the bounds for the integral in terms of u range between? Or at least, how would I find that out?
Would you plug in like -2 to the u function? And then
Exactly. When I plug in -2 and +2 into here, that tells me what's going to go in here, right? So when I plug in x equals -2, I'm going to get negative 2 squared. Well, -2, the quantity squared, is +4 divided by 2. I get -2 in the bottom. -2. Okay, so bottom one is the same. When I plug in the top one, I'm going to get -2 to the 4th. Well, or sorry, 2 squared. That gives me 4 divided by 2. The top one is also -2. Okay. So then what's this integral? Do we even, this is one example of why it's nice to just jump straight to another definite integral in terms of u, because what is this integral? The integral from -2 to -2 of e to the u.
Just 0.
0, exactly right. This is the area just over a single point. And we know that that's 0, right? So, but if we had done all the work of finding the antiderivative and then plugged in plus or minus 2, we still would have gotten 0, but it would have been a lot more work, right? So this is this is a method of avoiding that process of first finding the antiderivative and then plugging in. We're sort of shortcutting that, right? So any questions on this? All right, let's look at another one where it's not quite that nice in the end. It's still, I mean, it's still fine, but just, it's not going to be 0. Okay, so let's look at the integral from -1 to 4, or sorry, plus 1 to 4 of 6x plus 3 divided by x squared plus x. So first of all, is 6x plus 3 divided by x squared plus x, is that just some, the derivative of some function we know already? I would say no. Maybe you guys are smarter than me and know a lot more functions than me, but I would say no. So what would then, this is a u substitution problem. What would u be? This one's maybe a little harder to see. U should always be, what were you gonna say?
No.
Okay, you most of the time is going to be the most complicated thing that's happening in an integral. So what's kind of the most complicated thing that's going on in this integral?
x squared plus x.
That x squared plus x in the denominator, right? I'm going to make a guess, especially because this looks like it could be the derivative of x squared plus x times some constant. I'm going to make a guess. Let's say u is x squared plus x. Okay. Well, then what is du?
Two x plus 1.
2x plus 1, and then dx, yes. Very good. So, if we notice that if we multiply both sides of this by 3, so that 3 du is equal to 6 dx plus 3, or sorry, 6x plus 3 dx, then we have exactly what's left over, right? Or again, you could also just solve for dx and get dx is du over 2x plus 1. Plug that in and hope everything cancels, right? For this one, if you're not great with algebra, this might be one where you don't see that 6x plus 3 divided by 2x plus 1, that is just 3. Okay? So this becomes then the integral from somewhere to somewhere. We're going to find that out in a second. But 6x plus 3 dx, that is 3 du. Or I'll pull the 3 out in front. And then times 1 over x squared plus x. Well, that's 1 over u du, right? Okay, and now I just need to know what are the new bounds on my integral. Because again, I don't want to go through the whole process of first finding the indefinite integral and then rewrite it in terms of x and plug back in. Let's just shortcut that, do everything in terms of u. Okay. Again, in the language metaphor, well, why wouldn't you stick to your native language as long as you possibly can? And with definite integrals, we can definitely do that, right? So what's the new lower bound? How would I find the new lower bound?
Plug 1 into your u.
Good. I'm going to plug in 1 into here to get what this needs to be. And when I do that, I'm going to get 1 squared plus 1, that's 2. Okay. And then how do I get the new upper bound? Plug in 4, exactly right. I'm going to plug this in here to give me this bound. So when I do that, 4 squared plus 4, that's 16 plus 4 is 20. Okay. So then the only thing we need to ask ourselves is what function do I know that has a derivative of 1 over u? If you want, you can think of this as 3 times the integral from 2 to 20 of u to the minus 1 du, although I would argue that that's maybe a little misleading to do because we're not using the power rule for this, for integrals, right? Because the exponent is minus 1, which is the only case we can't use the power rule for integrals. So what would I get instead of using the power rule?
Could you get 2 over u squared?
No, because that would be, you're trying to use the power rule there, right? But we can't really do that because if you, the issue with doing that is we would get u to the minus 1 plus 1 divided by minus 1 plus 1, but that's dividing by 0. So the power rule doesn't work when the exponent is minus 1.
Could
But-
you do
Yeah.
like 1 over u is like the natural log of u.
Yeah, 1 over u is the derivative of the natural log of u. Exactly. So this is 3. Come on. Oh, I'm on the eraser. 3 times the natural log of u. Technically, when you take the integral of u inverse, it's technically 3 times the natural log of the absolute value of u. That doesn't really matter here because we're plugging in positive values. But then I get that I want to evaluate this at u equals 20 and u equals 2, right? So when I do that, I'm going to get 3 times the natural log of 20 is positive, so I can just put it in parentheses, minus 3 times the natural log of 2. Okay. Technically, you're done. Technically, that's a number. You could say I'm done on a final, for instance. You could move on from there and say, I'll come back to this if I have time, but this is technically an answer. Okay. We can do a little more simplification. This is, both of these have a 3 in common. I'm going to factor that out. This is 3 times the natural log of 20 minus the natural log of 2. And then what can I do with the natural log of 20 minus the natural log of 2? And don't say that it's the natural log of 18. What can I do with natural log of 20 minus the natural log of 2? This requires some rules for logarithms that you learned 1,000 years ago. Yes, we can divide the natural log of A minus the natural log of B becomes the natural log of A divided by B. Okay, so this is 3 times the natural log of 20 divided by 2. Okay, that's one of your rules for logarithms. And this is 3 times the natural log of 10. And then last, if you want to really write this in a simplified way, this 3 out in front, you can bring that into the natural log as an exponent, right? And so this becomes the natural log of 10 to the third, which is 1 with 3 zeros. So the natural log of 1,000. Amazing. Okay. Do we have any questions on that? Everything from, once we wrote this answer down, we were done, by the way. The rest of this was just simplifying in case you ever have to take an exam with someone who's giving a multiple choice exam and you need to make your answer look exactly like theirs. That's 6.9. Thank you, Saba. This is about 6.9. Okay. So we can look at the area under the, let's look at 6x plus 3 divided by x squared plus x. 6x plus 3 divided by x squared plus x from settings. X equals 1, 2, 4. Okay, so we were finding the area under this guy, right? No, don't. Oh, because I'm not on the axis. Okay, so we're finding the area under that guy, and it comes out to be about 6.9. Okay. Oh, should you on an exam? If I don't say round your answer, then I want an exact answer. I will tell you explicitly if I want you to round your answer to a certain number of decimal places. And so if that is missing, then assume I want an exact answer of natural log of 1,000. Yeah.
So when we're taking a variable and plugging in and
yeah,
we're not putting down in what was, which are the x's.
Exactly. Yeah. We're sort of just jumping over that step. Exactly right.
That's also getting rid of like the constants too, right?
Exactly. Okay. we have time to at least start this one. Let's look at this one. Evaluate the square root of x plus 1 squared, quantity squared, divided by the square root of x with respect to x. Actually, I'm going to call an audible and show you one more, just so you guys don't think U substitution is a one-trick pony. I'm going to show you one more integral where you might not think at first that U substitution would apply. So let's look at the integral of the square root of 1 plus x times x with respect to x. Okay. This at first doesn't look like something that we'd be able to use a U substitution on because, well, if this is U, with that x outside of that square root, that's not the derivative of the inside of this, right? But this is another place where U substitution is going to shine. The idea is, well, it would be really nice if this square root, if the square root was on this guy instead of on this guy, we could do this really easily because then I would just be able to use the power rule. If I was somehow able to move the square root, then this would be x to the 1/2 times 1 plus x. I could distribute stuff. So right now it is quite annoying. So the idea is, let's let U be 1 plus x. And this is a case where you're going to have to solve for x. Okay? So if U is 1 plus x, then x is U minus 1, right? And what is du? Well, if U is 1 plus x, then du is just dx, right? The derivative of the right-hand side is just 1. And so the du is just dx. Okay? Or dx is du, however you want to look at it. Okay, so I'm going to plug both of these in to my indefinite integral up here. I'm going to get the integral of, well, I have x square root of 1 plus x dx. Well, if I just leave the x there for a second, pretend I don't know what to do with it, then this becomes the square root of 1 plus x. The square root of 1 plus x is just u. And then dx is du. So by plugging in u and dx, I wasn't able to cancel out x perfectly. That means I need to substitute in x is u minus 1. Because again, I can't have an integral that's got mixed variables in here. Okay, so this is equal to this, which is equal to the integral of, well, x is u minus 1 times the square root of u. I'm going to write that as u to the 1/2 du. Okay. And then you can see, well, now exactly what we wanted to happen happened. We took the square root from over the sum, which is hard to work with, and we sort of moved it over to just the one single independent variable, right? And now this is the integral. When I distribute, I can just use the power rule. This is the integral of u to the, well, u to the 1 times u to the 1/2, that's u to the 3/2, minus 1 times u to the 1/2, that's just u to the 1/2, du. And so what do I get from this? What's the integral of u to the 3/2?
U to the 5/2 over 5/2.
U to the 5/2 over 5/2. Yes, and then minus, and right now I am breaking up the integral. You can do it piece by piece, right? So minus, what's the integral of u to the 1/2? U to the 3/2 divided by 3/2 plus some constant. Okay, and so this becomes this is equal to, when I simplify, this is 2/5 times u to the 5/2. Well, u was 1 plus x. Okay, and then minus 2/3 times 1 plus x to the 3/2 plus some constant. Okay, so this goes to show that you don't need a integral that looks exactly like that template that we had, f of g of x times g prime of x. U substitution can be applied in so many more ways. It just requires a little bit of cleverness sometimes to make it work. But in situations like this, where you want to move the square root from over that sum of stuff just to that individual x, U substitution works perfectly for that. You just need to solve back for x. Okay. All right, we didn't quite get through everything, but those last several slides, it was just going to be icing on top of the cake, so that doesn't really matter. We got through everything that I wanted to get through, really. So, if anybody has any questions, you can stick around and ask. I have office hours today, 1 to 3. Come in and talk to me then. And then quiz after class, I'm going to open up in the next 15 minutes. So other than that, everybody make sure to have a fantastic Thanksgiving break. And I'll see everybody in some form after the break. Thank you, everybody.
Break. Have a
Thank
good break.
you. Happy Thanksgiving.
Thank you.
Yeah,
Happy Thanksgiving.